Okay, so last two things to cover: polynomials and functional equations. All right, so a polynomial is an expression in terms of x of this form, where the a0, a1, etc. to an are constants. Right, those constants could be real, or they could be integers, or anything. Right, n is a non-negative integer. It could be 0, it could be positive, but it could never be negative. Right, so a root or 0 of that polynomial is a value of x. You could say, for example, x is equal to alpha that satisfies that is such that when you substitute that value into the polynomial, you get 0. Right, meaning a value of x that makes this entire expression equal to 0. So for example, for this polynomial, there are two roots. So x is 1 and x is 2. You could substitute those and see that you get 0. All right, now the degree of the polynomial basically is the highest power of x. So it's whatever this value of n is, n is the highest value. All right, so first, if p of x is 0, it's called the 0 polynomial, and the degree is undefined for that, right? The 0 polynomial doesn't have a degree. If it's a non-zero constant polynomial, all right, so for example, p of x is a0, where a0 is not 0, sorry, then this is it's said to have a degree 0. All right, just remember, 0 polynomial has no degree defined. So if the degree is 1, it's called a linear polynomial. Degree 2 is quadratic. Degree 3 is cubic, and so on. You could have degree 4 would be a quartic. Degree 5 would be a quintic, and then beyond that, you don't really want to start naming them. These two properties are useful to know when you're talking about the degree of a polynomial or two polynomials. So if you take two polynomials, p and q, and you add them, the degree of that sum is less than or equal to the maximum value of the degree of either. Right? Usually, so if they both have, let's say the degree of p of x was greater, then the degree of the sum would be the degree of p of x, right? The maximum one. The only time it's less than is when they have the same degree and the coefficient of, say, q of x is negative, the coefficient of, the coefficient of x to the power of n in p is negative, the coefficient of x to the power of n in q, so when you add them, it cancels. That's the only time the degree goes down when you add polynomials. Every other time, the degree would stay the same as the highest one. When you multiply them, the degree adds. So if you take, for example, if this was like a second degree and you multiplied it by a third degree, then the degree would be just the sum of the degrees. So 3 plus 2, you'll get 5, right? Because when you multiply x cubed by x squared, the power is x to the power of 5. So you sum the degrees when you multiply polynomials. Two polynomials are equal if they have the same value of, well, if the polynomial gives the same value for each value of x. Right, so for example, if p of x is x squared plus 1 and p of x is x squared plus 4, then if I take x is 0 or x is 1 or x is minus, well, actually, yeah, so if I take x is 0, yeah, and x is 1 and x is minus 1, it'll give me the same value for both polynomials. So for 0, I'll get 1 for both. For 1 and minus 1, I'll get 2 for both. Right, but that doesn't mean that they are the same polynomials, because actually if you take x as 2, you'll get different values. Right, there's some theorems here now. Fundamental theorem of algebra says every polynomial with complex coefficients, meaning that's what we're concerned. So every polynomial basically with degree greater than or equal to 1 is going to have at least one complex root. Right, and even further than that, if a polynomial has degree n, then it has exactly n complex roots. These are not necessarily distinct. Some could be repeated. And the
question.
Yeah.
When you say exactly n complex roots,
yeah,
like you're considering real roots complex.
Real, real is a subset of complex.
Yeah.
So yeah.
All right, it was just a little confusing.
Yeah. So real numbers are a subset of complex numbers. So when we say complex here, we're just being as general as possible. This includes real as well. All right. So this includes it includes ones with imaginary components. It includes distinct real roots, and it includes it includes repeated real roots as well, the 3 possible cases. So if a polynomial has degree less than or equal to n, and it has at least, so basically, if the number of roots or the number of distinct roots is more than the degree of the polynomial, automatically that means the polynomial has to be the 0 polynomial, right? Because there is no other polynomial could have more roots than the degree of the polynomial. That doesn't make sense. And similar to that, if 2 polynomials have degree n or less than or equal to n, and they have the same value at least n plus 1 distinct values of x. So basically, 2 polynomials, the degree of both of them is less than or equal to n. And for n plus 1 distinct values of x, they have the same value for the polynomials. It means they're equal, right? Because how you would show that is you would define a third polynomial to be the difference of these two. And then it means that that third polynomial would be, the degree would be less than or equal to n. And it would have n plus 1 distinct roots, because if they have the same value, then the difference would be 0. So those values of x would be roots of the third polynomial. And then you just use this one, and it gives you that it must be a 0 polynomial. So if the difference is the 0 polynomial, it means that they're identical. So the remainder and factor theorem kind of go hand in hand. So when p of x is divided by x minus a, the remainder is going to be p of a. Right? Meaning if you long divide a polynomial by x minus a, you will always get the same value in the end as if you had just substituted a into p of x as a remainder. And then the factor theorem says, well, if x minus a is a factor of the polynomial, right, then it's kind of related to this, right? Because if x minus a is a factor, you're not going to have a remainder. Your remainder is going to be 0. So x minus a is a factor if and only if the remainder is 0, or if and only if p of a is 0. All right, an example here, find all quadratic polynomials p of x satisfying these 3 properties. So we know p of x is a quadratic. It means the degree is 2. Now from this, you could say, well, let p of x be ax plus bx plus c, and then try to solve. You have 3 conditions. You could solve for those simultaneously. But before you do that, this condition could be used to simplify the problem a lot, actually. So if p of 2 is 0, it means that x minus 2 is a factor of the polynomial, right, by the factor theorem. So rather than writing p of x as ax squared plus bx plus c, I could write p of x as x minus 2 times some linear polynomial, right? Because if the degree of the polynomial is 2, and I take a linear here, I must have a linear here so that when I multiply them, the degree becomes 2, right? So therefore the constants, I only have 2 constants now, a and b. All right, now you could multiply this out, but really and truly you shouldn't expand things unless you have to. What you could just do is directly substitute x is 0 into this, and then x is 1, and you get your answers. Right? And then after, if you want, you could multiply this out and you get your polynomial. All right, so just a little more discussion on quadratic polynomials. So again, general form of a quadratic is ax squared plus bx plus c, where the first term a is non-zero. Right? If this was 0, then you wouldn't have a quadratic. All right, so you can do 2 things with this. You could complete the square. All right, so I hope everybody knows how to complete the square. And then you can also look at the quadratic formula to get the solutions. This term inside here is called the discriminant. All right, b squared minus 4ac. So if this is less than 0, you're not going to have real roots, right? Because you have square root of a negative number. So you're going to have complex roots. If it's equal to 0, basically your answer is just going to be minus b over 2a. So it's going to be a repeated root. That root minus b over 2a will be repeated twice. And if it's positive, then you're going to have 2 real distinct roots. Right? So that's how we check to see what the roots are. And then we come to Vieta's formula or Vieta's formulae, which you may have used without seeing the name. So basically what this does is it relates the roots of a polynomial to the coefficients of the polynomial. So we could start by considering a quadratic polynomial. P of x is ax squared plus bx plus c. Assume the roots are alpha and beta in any order, right? Now what Vieta's formula says is that if I take the roots and add them, a plus b, I'm going to get the same as alpha plus beta. I'm going to get the same thing as negative b over a. And if I multiply them, I'll get the same as c over a. All right, so this is what Vieta's formula says. So you could look at this example here to see that it is in fact true. You could expand that further. It's not explicitly listed for cubic, but for cubic, so if you had a cubic, right, ax squared plus bx plus c plus d, so ax squared plus ax cubed plus bx squared plus cx plus d is a cubic, and you let alpha, beta, and gamma be the roots, then alpha plus beta plus gamma, because there's a third root, would be equal to this. But then in the second line, you would have alpha beta plus alpha gamma plus beta gamma is equal to this. And in the third line, you would have alpha times beta times gamma is equal to minus d over a. Right? So this is the more general version. Right? This is I guess you could look at this for the case of a cubic. So the roots would be alpha, beta, gamma. So you have alpha plus beta plus gamma is minus b over a. Alpha beta plus alpha gamma plus beta gamma is c over a. And then alpha beta gamma is minus d over a. It's always nice when a is 1 because you don't have fractions. It's just numbers, just integers. Right, but this is the more general case. So how it goes is, let's see. So I want a general polynomial. P of x is a n x to the n, and you keep going. So in each of these equations, you start with the first coefficient is a n. You always divide them by a n. So you start with the second one. You go minus a n minus 1 and divide by a n. Then you go and you alternate sign. So minus plus minus plus. And the next one will be a n minus 2, then a n minus 3, and so on until you get to a0. Right? So if it's an even, let's see, if the degree is even, you're going to have an even number equation, so the last one will be a plus. If the degree is odd, you'll have an odd number equation, so the last one will be a minus 1 here. Right, and then on this side, how you go is the first one is always the sum of the roots. Alpha, whatever the roots are, you sum them. And then the second one is the pairwise products. So you just multiply pairs at a time and then until you have all the pairs and add that. And then you go 3 at a time and then 4 at a time, depending on if you had that many. And then the last one will always be the product of all of them. Right, so that's Vieta's formulae. There aren't any examples showing you how you use them, but when you work on these problems, you'll see how they come about. Right. Any questions on this so far? I know we had kind of done some of these things before, so it's like repeating what you already know kind of thing. Right, what I want you all to do is attempt all these problems, right? And then you have the hints, so you could actually look at it if you want. But also, if you want, we could take a day and just kind of go through the solutions to all of them, so you see, or I could explain if you have any doubts about any of the solutions. Okay, now the last thing to cover is functional equations. So I have here a short write-up on functional equations, which we'll go through, but then I want to go through some more things on functional equations that I have in a separate file that I'll post up on the website as well. That's the file that we used for the camp last year. So it has is more detailed than what the other one has. right? But let me start with the one that you've already seen. So a function or a map, so a function f basically it takes a domain A and maps elements in A to another domain B, right? So it's a map between the two sets A and B, and it assigns a unique element in B to every element in A, right? So the set A is referred to as a domain and the set B is referred to as a range, right? Now, not all elements in B will necessarily have an element mapped from A to it. And we'll talk about that just now, right? Every element in A gets mapped to something, but not everything in B is necessarily mapped to from an element in A. All the elements in A could be mapped to a subset of B, right? And in that case, if it was mapped to a subset, we call this subset the codomain. All right. Where is this? So if there's an element in A that's mapped to an element in Y, we say f of x is equal to y. Now, some examples here. So if you take a function mapping from the set to itself that maps every element in the set to itself, basically f of x is equal to x. This is called the identity function. Basically, you take an element and map it to itself for every element. You can also have a constant function where basically you take every element in in A, and you map it to some constant in B. Right. So in this case, everything in A gets mapped to a single value in B. Right, and you can have other functions like this defined here. So h of x is x squared, maps every real number. Now this is from reals to reals, right? So it takes every real number and maps it to the square of that number. So to be more precise, the real number, I could have replaced this with r star, right? Because technically none of the negative numbers are mapped to. So you could actually adjust the range if you want, depending on what the function is. Similarly here, this could also be r star because it's k of x is absolute value of x. These are always non-negative. Some things to note here. Every element of the domain must be mapped to some element in the range, but not every element in the range must have an element mapped to it. This is what I explained before. So in the examples here, so I'll use f, g, h, and k defined here as examples to illustrate these points. So h and k, so for these things, the negative elements don't have anything, the negative elements in the range don't have anything mapped to them, right? But for these, well, these we don't already know what A and B are, so we can't really talk about those yet. Next one, if every element in the range does have an element mapped to it, right? So if everything in the range has something mapped to it, then we call the function surjective or onto, right? You would probably be more familiar with the term onto rather than surjective, but this is a more formal name, right? And the mathematical representation of that is basically saying for all y and b, there exists an element x in A such that f of x gets mapped to y, or f of x is equal to y, x gets mapped to y. Right, so this function in example 55, f of x, this is surjective, right? Because everything in A has something mapped to itself. So everything is mapped to. These two are not surjective because, like I said, the negative ones don't have anything mapped to them. Right. Any given element in the domain can only be mapped to one element in the range, but a given element in the range can have multiple elements mapped to it. Right, that's important. For a function, basically, you can't have the same element in the domain being mapped to two elements in the range. That doesn't make sense. It has to be a unique mapping. But, for example, if you consider this one, right, x is 2 and minus 2 both get mapped to 4. So you can have an element in the range that gets mapped to from two different elements. That is possible and it's okay. So you could go from one element to this and then another element to the same element here, but you can't do it the other way. You can't go from one element to two different things. Right, so we talked about surjective. We also can talk about injective. So this basically what injective means is that when I talked about having two elements mapped to the same element, if that happens, it's not actually injective. If it doesn't happen, then yes, it's injective. Meaning, basically, if any given element in the range has no more than one element mapped to it, meaning it's a straight line. You don't have things linking to the same element. Each element gets mapped to a unique element. Then the function is said to be injective. So mathematically, what that says is that if f of, meaning if x1 and x2 are mapped to the same element, the only way that could happen is if x1 and x2 are actually the same element themselves. Right? So how you would prove something is injective is assume that two elements get mapped to the same thing. So prove that x1 and x2 get mapped to y, and then show that x1 and x2 are actually the same thing. That they must be the same thing. And that means it would be injective. Now, when something is onto and one-to-one, or surjective and injective, if it satisfies both of those, then we call it bijective, right? And if it's bijective, it means it has an inverse. So there's a function that goes back to the reverse way. But if it's not bijective, then we don't know that's true, so you have to be careful. All right, equality, addition, subtraction, and multiplication, those things are straightforward. Composition of functions, be careful with this. Right, so composition basically is where your f maps elements from A to B, and then another function maps the element from B to another set C. Normally, when you represent composition, right, normally it would be written like this rather than using a symbol. So, and even sometimes even we would even forget about the bracket. We wouldn't bother to write the bracket. So sometimes you might just see things like this, GF or FG. This doesn't mean G times F, right? It means G of F. So be careful with that. Right? If it was multiplication, you would see it would be written explicitly as G of X multiplied by F of X, or G of X, F of X. If you see G, F, and then X in brackets, it means that this is composition of those. And composition works right to left. So you find F of X first, and then you find G of that. So two definitions here for even and odd. So it's even, it's an even function if F of minus X is the same as F of X, meaning that it doesn't matter whether X is negative or positive, as long as it has the same magnitude, it'll have the same function value. And then it's odd if the function value for the negative ones is negative the function value for the positive ones. So examples of this, so an example of an even function is F of X is X squared, right? Because for X squared, if I substitute X or negative X, I still get X squared. So that's even. Also, cosine of X is even, or any X to any even power would be an even function. For odd, you could take X to any odd power, right? Because for example, X cubed. If I put in minus X in there, I'll get minus of X cubed, which is the positive one. And sine of X is also an odd function, right? So these are the examples here, right? But like I said, X squared, X to the power 4, even a constant function, those are all even functions. Any odd power of X is an odd function. Be careful though, when you combine them, it's not necessarily the case. So if I had like X squared plus X, that is neither even nor odd, right? It could actually be neither even or odd. It can't be, well, the only thing that could be both is if it's basically 0, right? If it's a constant function equal to 0, then that is both even and odd. But everything else is neither. Well, sorry, everything else is either even or odd, or neither even or odd.
A question.
Yeah.
So how is a constant function that's not 0 even?
Because no matter what, the function is the same for everything. So if for example, if I took f of minus 1, I would get a constant. If I get f of 1, I'll get the same constant, so they equal.
Right. So by that, shouldn't f of x equals 0 be an even function as well?
Yeah, but it's also odd. Because
Oh, if you take the negative, it'll still wait.
yeah, it will still be there.
Yeah, it'll still be 0. Oh, okay.
So it
Right.
satisfies the f of x is equal to 0 satisfies the conditions for both.
Right, I see it.
But it's the only function that does that.
Okay, cool.
Yeah. If it's a non-constant, sorry, if it's a non-zero constant function, then it's only even. Right, and the reason, well, that kind of ties back to what we talked about degree, right? So as I mentioned, if it's an odd degree, then it'll be an odd. If it's an even degree, it'll be even. But remember, non-zero constant functions are even degrees because the degree is 0. But the zero polynomial doesn't have a degree defined. So that's why it falls into both. But that's why it is possible for it to fall into both. All right, so a functional equation is basically an equation involving one or more unknown functions that you have to determine. Usually it's to determine the functions themselves, sometimes it's to determine properties of the functions. Right? In order to solve that, you need to determine the functions that are satisfied, but you also have to prove that those are the only ones that do. Right? And you have to actually prove they do. So you need to have correct reasoning as to why other functions do not work. And you have to verify that the function you say works actually works. Because sometimes you can go through some steps in the working and get a function, but then that function doesn't satisfy the condition. So it's the same thing with the implications. If you start with an equation, you could get some implications that imply certain functions must be there, but that function doesn't necessarily actually satisfy the condition. So you have to always verify. This, with functional equations, is even more important than with other things. You always have to verify your functions. So the main strategy for solving functional equations is to substitute values and see what happens, right? It's not just substituting values, it's substituting other things as well. Let me see. Okay, so we could go through this and then I'll look at a more advanced version of this after. So we'll do this and then take a break and then finish off that part of it. So first thing we could do is substitute values in the domain. So for example, usually you would try to figure out what f of 0 is, or f of 1 or something like that. So it might be useful to substitute x as 0, sometimes 1 or minus 1 or things like that. The idea here is if you could figure out what f of 0 or f of 1 is, sometimes you could make substitutions using that to simplify the equation into something you could solve. Apart from just substituting values, you could actually substitute expressions. So now this is a key thing I want to point out with functional equations. If you see x and y as variables, or even just x or whatever, in a functional equation, always remember that those things are dummy variables. Meaning you could interchange x and y, or you could let x be something, or you could let y be something, and it doesn't change the validity of the equation. But just be careful to make sure you stick within the domain, right? So for example, you could substitute things like y is equal to x, or y is equal to minus x, or y is equal to 1 over x, but you can only use 1 over x, right, if it's real numbers you're looking at. For example, if it's integers, it doesn't make sense to do this because that is not really valid. If it was positive real numbers, then substituting y as minus x also wouldn't make sense because you can't have negative numbers in there. And if you use y as minus x, then basically if x is positive, y would be negative. So if the domain and the range are the same set, then using recursive relations like this, y is equal to f of x, can be useful. So usually that is the case. Usually you're talking about real numbers to real numbers. So you could do things like taking y is equal to f of x, right? And it might not be obvious right now how this will help, but we might see some examples with that just now. Introducing a new function can also help simplify the problem. For example, if you try some functions or you just play with it a little bit and you realize that, or it seems to you that f of x is equal to x is the only solution, or maybe it's a solution and you can't seem to find any others, then what you could do is try defining a new function as g of x as f of x minus x. Now, if g of x is f of x minus x, and you want to prove that f of x is equal to x is the only solution, what you need to do now is prove that g of x is equal to 0, which might be easier to do than actually doing this, than working with this. All right, so that's one thing, another strategy you could try there. All right, so this is why I mentioned about the dummy variables, so you can interchange them and do anything you want with them. All right, yeah, so we'll actually look at this just now, the advanced strategies. Some simple examples first. So find all functions from reals to reals such that f of x plus y plus 3 times f of x is equal to f of y. All right, x and y are real numbers. All right, so, well, the solution is there, right? But I mean, if you look at this equation, right? If you take x, or if you take y as 0, all right, substitute y as 0, you'll get, basically, you'll get f of x plus 3 of x will be 4 f of x is f of 0. Right? Or, well, either y is 0 or x is 0, you'll get the same thing, basically. So let me explain it using this way. So if I take x as 0, then I'll get f of y plus 3 f of 0 is equal to f of y, right? I could just subtract f of y on both sides and I get 3 f of 0 is equal to 0. So automatically f of 0 must be 0. Now, once I know f of 0 is 0, then I can come and say, well, okay, let me substitute y as 0 because this will go away. All right, so substitute y as 0 and then I get this. So basically it means that f of x must be 0. Right. Now, again, this implies f of x is 0, so you still need to verify that. Now, for the verification for this is easy because, I mean, if f of x is 0, then everything becomes 0, which works. All right, a couple more questions here. So find all functions from reals to reals such that f of x squared, meaning f of x times f of x, is equal to f of x plus y. Right. So again, usually you try to see what happens when x is 0, y is 0. So if you take y as 0, then you'll get f of x squared is equal to f of x. Now be careful with this. You can't just go and cancel f of x, right? Because if f of x was 0, then you're losing a solution. So what you should do is bring this across, never cancel. Bring this across and factorize, and then take cases. Either f of x is 0 or f of x is 1. But again, you have to be careful with this, right? This doesn't mean that f of x is exclusively either 0 or 1. It could be that for some values of x, f of x is 0, and then for the other values of x, f of x is 1. So that's something you have to be careful with. Right? So for example, I could have defined a function that says f of x is 0 for all rational numbers and f of x is equal to 1 for all irrational numbers. And that would satisfy this. Right? Regardless of whether f of x is rational or regardless of whether x was rational or irrational, I would always get 0 in the product. Now, what I have to actually do is prove that that doesn't happen. So I'm not done yet. I have to show that f of x is either strictly 0 or strictly 1. So to do that, what we're going to do is, we must show that it doesn't have any values such that f of x is 0 for some and then f of x is 1 for the others. All right, so suppose, let's take the first case. Suppose f of k is 0 for some integer k, right? We're considering the case where we have one of this happening. F of x is 0 for some x, so let that x be k. So f of k is 0, we know that. So let's use that. We're going to substitute x as k because I know f of k is 0. That'll help me here. So we know that the right-hand side was x plus y, so you get k plus y, f of that is 0 basically. Now, y could be any real number, right? Remember dummy variable. So I could replace y with x minus k, right? X minus k is a real number. So if I replace y with x minus k, I basically get f of x is 0. And now this x is any real number. So basically what that says is if f of k is 0 for some k, f of x is 0 for all x. All right, similar idea here. So I won't go through this one. It's the same kind of thing you're doing down here. All right, this one is an example showing that there is no solution. All right, so you all can go through this one. Basically, you get two contradictory things. Here, you substitute x is 1, you get f of 1 plus f of 2 is 1, then you substitute x is 2 and you get 2 instead. All right, and if you subtract, you'll get basically 1 is equal to 0, which doesn't make sense. All right, so